Hi, everybody. Hi, everybody. Great to see you all here. As you may have noticed, the title that I originally had for my talk is a bit different from what's up here. That's because as this workshop progressed, I got a better understanding of what metacognition even is, and then I realized that there's actually a deep connection between some of the work that we have been doing on formal methods for machine learning and the main themes of this workshop. So I changed some of the content. So the setting that we are going to start with is of deep learning agents. And here, the picture is something like this. You have a policy that is interacting with the world, and this policy is given to you as a neural network, and the traditional learning objective in this setting is that you are trying to maximize the agent's reward. Now, actually, we're not just going to talk about settings where the policy is just a neural network. We are actually going to think about these neuro symbolic agents where your policies are actually a mix of traditional symbolic code and also machine learning components, specifically neural nets. And the reason for this is that we are very interested in the creation of these closed loop systems where you have combinations of these neural networks and also classical code. And in particular, we have been looking at these applications in software systems, for example, network protocols and operating systems. And here's one example. So this is a classic, an extension of a classic congestion control algorithm. So it's the kind of stuff that keeps our networks working. Recently, there was this extension to a classic congestion controller called TCP cubic, where they added a neural controller on top of the traditional controller. And basically, the idea is that you're monitoring how clogged the network is, and based on this, you are deciding how much data to send out, how many packets to send out. But traditionally, this was done using a handwritten heuristic. But now you are adding on top of that this extra neural piece, which is really being combined with the traditional heuristic, and it's adding a little bit of extra flexibility. That is. Okay. Yeah. So the impact of this is that the controller is now a lot more flexible. It can make decisions that are much more data-driven. But now, whenever you're going to do things like this, there are going to be these questions of correctness. Okay, so you have stuck now a neural network into your congestion controller for your network. What's to make sure that your network is now, still going to behave at least reasonably? And this sort of application, and there are many others like this, they motivate this problem of learning under worst-case constraints. So now, in addition to the usual reward objective for the agent, you have this additional constraint which captures things that just cannot be violated. So there are many variants of this problem. For example, you can imagine that there are certain cases where if you just satisfy this constraint heuristically, you'll be okay. There are going to be cases where you want more. You want to have certificates that you are actually satisfying these properties. There are worst-case versions of this problem, probabilistic versions of this problem. You may want to satisfy the constraints at convergence or during training, so there are lots and lots of different variants of this. Just to connect this back to the application that I mentioned, so here are some examples. So for example, you can talk about safety properties that say that if the agent is experiencing high packet loss, it should decrease the send rate, because otherwise the network is going to just go down. Or liveness properties that the controller should not get stuck at a certain rate when the network is behaving well. It should try to get better performance out of the system. Okay, so you have these kinds of properties. Now, how does all this connect to metacognition? And this is what I sort of came to realize yesterday, because before that, my understanding of metacognition was, I think, a little bit incomplete. So I think that the way metacognition connects to this is that now you can imagine having a checker of the sort that formal methods researchers have built over the last many decades as part of this learning loop. So you can imagine now the agent basically using the formal verifier to check its properties as the learning is going on. And based on this, it's going to update its decision making. And so that's the overall idea, right? So now how do you actually instantiate this? There are many possible ways, and what we'll see is that for this particular, or for this situation where you have a neurosymbolic program as the policy and you want to do certain kinds of correctness checking, there are some nice ways of connecting classical formal methods with learning. And so I'll give you one example of this. So this is called differentiable symbolic execution. It follows the line of work on differentiable verification that's been done by several groups, including mine, but also, for example, Martin Fechev's group in ETH Zurich, they have been looking into that. And the starting point over here is that you are going to do verification of neural networks. Now, ultimately, neural nets are just a kind of circuit, and so all of these methods for formal verification that have been applied to, say, digital circuits over the years, you could imagine applying them to this context as well. And so a few years back, we did some work on applying a particular kind of classic verification technique called abstract interpretation to neural networks, to the verification of neural networks. And so the basic idea was that you're taking a neural net, you are representing it as a sort of a program, which is a composition of a bunch of simpler functions, such as convolutions and max pooling and so on. And then you are doing abstract interpretation on this. So what is abstract interpretation for those of you who are not familiar with the term? The basic idea is that you're executing the program not on a single concrete input, but on a symbolic representation of a set of inputs. So a simple example would be something like an n-dimensional interval, right? So you have n variables, and so you have ranges for each of the variables, and you have this n-dimensional rectangle that's capturing a set of possible inputs. Now, of course, you could say that, but why is the input representable in that form? Well, the idea is that you are doing an approximation. You are over-approximating the set of inputs that can actually arise by this sort of an interval, what we call interval abstraction. And then as you're pushing this interval through the program, in this case, through the layers of the neural net, the shapes are changing, right? So you might start with a rectangle, but it may become a polytope, or if you're using nonlinear things, maybe even something more complex. But the idea is that at each state, you are doing this sort of over-approximation to bring it back to this representation that you can easily manipulate, which in this case would be intervals. So for those of you who are familiar with interval arithmetic in numerical mathematics, this is just a generalization of that. So you don't have to necessarily stick to intervals in particular. You can also use polytopes and other kinds of shapes. Okay. So the good thing about this is that you get this certificate of safety after you have done this process. So if you, basically what you would do is that you would push these worst case sets through the layers of the neural net, and you're going to show that at each point, certain properties, certain worst case properties are satisfied. And because you're always working with over approximations, you have the guarantee for many kinds of properties that if you come up with such a certificate, such a proof, the property will actually be satisfied. Okay, so now connecting this back to learning, the idea then, and this was not our work, this is something that Martin and his students did at ETH. So the idea now is that you can use this abstract interpreter as a loss function. So how do you do that? Here's the basic idea. Imagine that you have this neural net, which in our case is this policy. And now for a second, let's only think about these purely neural policies. So you have pushed this, this set through this policy, and let's say that you're looking at the point where you have done the pushing. You're looking at the output set. And the output set looks like this. So what you could then do is that you could use a distance function from the set of unsafe states. So let's just say that the correctness property we're interested in is that we want to avoid some set of bad states. This can be generalized. So you can then use a distance function between this set and this set and use that as a loss function, right? So basically, what you would want, or here you're maximizing, so it's not quite a loss, but more like a function, a distance function. So you want it to be, this set to be as far as possible from the set of unsafe states. And because the policy is differentiable, the neural net is differentiable, this function is also going to be differentiable. And then you can feed it back into the learner. Now you see that this is already then giving us a sort of metacognition, because now you can imagine the agent maximizing its reward by interacting with the environment, but it can also periodically invoke this verifier to go and check whether or not it is satisfying these worst case properties. And while it's doing so, it's not particular to any input. It's really executing itself on all possible inputs, doing symbolic reasoning about itself, and then using that to update its parameters. Now, it turns out that this idea can be generalized to more complex systems, such as the sort of neurosymbolic systems that I showed you earlier, where you have this sort of a composition of symbolic code and neural nets. And so the basic idea would be something like this, that, and this is something that my student Chen-Shi Yang developed in this iClear paper from last year. And so the basic idea over here is that you're going to model the system as this sort of a stochastic computation graph, where you have so all these branches and function applications, all of these kinds of control constructs that you have in programs. You're going to just construct a computation graph out of that. And then you are going to do abstract interpretation through this thing or some other kind of symbolic verification. And then you're going to push these gradients back through this graph, and that's going to be the overall idea. Now I'm going to show this to you in a little bit more detail. Just wanted to give you an overview. So just to at this high level, imagine that you are starting with this kind of a green rectangle at the top. This is a large set of inputs. And then you're basically doing what PL researchers or formal methods researchers would call symbolic execution. So you are pushing these sets through different paths in the program. And for example, if you're starting with this big green set, some part of that set is going to satisfy P, some part of it is not going to satisfy P. And so you're going to push these two different sets along the two branches, and this process is going to go on. And then by the time you get to the end, there are going to be losses, and then you can compute gradients of that, and then you can push them back through the program. That's the overall idea. And there are details over here. So just to make this a little bit more concrete, so here's like an example of a program where you have a loop and you have some neural nets. So this is modeling a simple thermostat, which is controlled by a neural controller. And so you have some neural control modules, and so that would be that pi theta cool. And what it's deciding is whether or not the thermostat is on or off. And then there are some dynamics equations that tell you, if the thermostat is on, how much heat is being put in, how the temperature is changing, and so on. And so the thing to note is that here you have loops and you have branches, so you have a lot of complexity. And so what this approach that I described, what that would do is that it would, basically start with the symbolic input. It's going to push it through these different branches. And so just as an example, along the left branch, what's going to happen is that it's first going to truncate the set, and then it's going to apply the function to that interval, and this process is going to go on. So the two issues that you're going to face are that, first of all, there's going to be this explosion in the number of possible paths that you have to take. And the second is that you're going to have these non-differentiable operations because of the discrete branches, like if you have this if then else's and while loops and so on. So these are in general non-differentiable. And so what you do is that you use a stochastic approximation. That's what we did over here. But there are other kinds of strategies that you could do as well. And so, concretely what that means is that when you have that if then else kind of a situation, rather than just modeling it as a discrete branch, you basically model it as a weighted sum. So you look at the volume of the set that goes down the left branch and the volume of the set that goes down the right branch, and you basically take an expectation over these two. So what that will mean is that you are going to be putting more weight on the paths that have most of the cases. Now, there is this question about whether or not this captures this absolute worst case culture that we have in formal methods, but this is what makes the thing scale. And so once you have made this kind of a smooth approximation, it turns out that you can there are still some complexities, but you can basically bring in some ideas from reinforcement learning, and you can do backpropagation through the resulting graph. So essentially what you're doing is that you're replacing the discontinuous statements with these probabilistic sampling statements that are weighted by how likely each of the paths are. So this is just the starting point for this kind of research, and what we found so far is that the results are pretty good. So here, let's just focus on the graph on the left. So what we are doing over here is that on the y-axis, you have the fraction of the cases. So you have the input, you're breaking the input up into a lot of little pieces, and you're asking for what fraction of these starting points can we actually provably guarantee safety. And so what we are finding is that this method where you're explicitly invoking a verifier from within the learning process, it gives you a correctness guarantee, a certificate with a certificate pretty quickly. So you need still some amount of training data to get to that point, but that works out. And so what that shows is that this idea is generally promising. Now, of course, there are challenges. For example, how do you really scale this sort of thing to much more complex systems? And we are currently working on deploying these ideas in this network setting that I showed you earlier. Now, there are other angles here that I didn't really address. So one is that this policy in a classical reinforcement learning setting would be actually interacting with this external world. And this world is going to be a black box. But then how do you verify, how do you do this kind of formal reasoning techniques when you have this black box world that you're interacting with? And so we have some recent work where we combine verification with model learning. So, model-based RL is a thing. It's usually justified by scalability. If you have a model of the world, then you're able to just simulate a lot of interactions effectively. But another benefit of having a model of the world is that you can then do verification with respect to it. You can do symbolic reasoning with respect to it. And so that, I think, is also a generally interesting idea in this context of metacognition, that if you have an agent that's interacting with the world, learn a model and then do reasoning with respect to the model when you are doing when you're checking your state. So I won't go into the details. We have a paper up on arXiv that you can look at if it's of interest. But basically, there are some clean guarantees that work out. You have something essentially probabilistic in this case, because the model that you're going to learn about the world, that's going to be probabilistic, right? I mean, it's learned after all. And so any guarantee that you're also going to get is going to be probabilistic then. But if you're willing to live with that, then this would be a good idea. And then another question is that we would frequently get when we talk about connecting formal methods with machine learning is that, okay, this is all machine learning pre-2020 or pre-2019 or whatever, right? So what about very large models, the kind that we have heard about a lot today? How do we do verification of GPT? And the answer is that we just don't, right? We can't. So we have to think about alternative strategies for applying this kind of idea in the context of very large models. And so a natural approach in this kind of a setting would be to do shielding. And what is that? That would be that you are not actually trying to verify something like GPT-4. Instead, you are monitoring its behavior, and you have a way to fall back on a provably safe function, in this case, a provably safe policy, if this very large neural network that you have is behaving in a way that doesn't seem safe. And so this would be what that looks like, that I can write it as code. So if my big neural net is taking an action that is unsafe, then I'm going to fall back on a program that's verified. Otherwise, I'll just let it execute. And we have a line of work where this idea is developed quite a bit. Rather than just using a single fallback program, which would be inefficient, you have a range of possibilities to choose from. And so the basic idea is something like this. Imagine that you have this set, which is all possible functions that you can use to execute in the world. So this is the set of all possible policies. And you have a subset of that. That's the set of verified policies that are going to be less efficient for you because these are probably going to be simpler programs for which you can actually do verification. But the bigger class is basically all possible neural or neurosymbolic functions. And so it turns out that this problem of learning a function that looks like this, where you have this kind of an if-then-else, where you are going to fall back on a verified program if your neural component, large neural net, is not behaving well. So it turns out that that problem can be cast as a sort of a mirror descent, which is a generalization of projected gradient descent. And so the basic idea is very simple. You are going to do gradient descent in the space of all of these policies, and what you're doing is that you are updating. You're taking these gradient updates. So imagine that you have a safe policy, which is the backup, the fallback, the shield, and you have a neural net. Something like maybe not GPT-4 because it's a black box, but imagine you have GPT-2. So you have that pi, which is the pi component, which is a neural net, and the f component, which is a verified program. And so what you're doing is that you're applying updates to these neural components, and you do that for a while, but then you project it back to the set of verified policies. And so what that means is that you're updating the symbolic part of that program. So basically, you're dovetailing updates to the neural component, which would be in this case updates to GPT-2, let's say, and updates to the shield that you're falling back on should GPT-2 behave unsafely. And so it turns out that the overall problem of the overall learning problem, how can I get an optimal shielded policy, it can be cast in this kind of a framework. And it comes with nice guarantees and everything. Now there is this one little piece, which is that how do you actually do this project operation? Like I have a neural net, I have GPT-2, and I have a symbolic shield. how do I project back to the set of verified policies? So what that means is that you are trying to find a purely symbolic function that is as close as possible in behavior to this kind of a hybrid, shielded thing. And that in itself is a program synthesis problem, but it turns out that there are some strategies for solving that. I can talk about that more to you afterwards, if interested. And so the higher level point that I want to make over here, though, is that this idea of connecting formal checking within the loop, right, with machine learning. This is something that's a very powerful idea. It is something that can be implemented in many different ways. One idea is to just have directly gradients from the formal verifier. This is what I showed earlier. But you could also imagine this kind of shielding approach, which doesn't require any neural net verification. Okay, so this approach, there is no neural net verification in any of this. You are getting a verification guarantee, but what you're doing is that you are treating the neural net essentially as a black box. You are abstracting it out, right? And what you're saying is that no matter how it behaves, you're going to have this correctness guarantee because you have this thing to fall back on, this verified program to fall back on. Yes, it's not going to be as performant as a neural net, but it's going to be safe, and hopefully you won't have to use it too often. And you have some convergence guarantees about the whole algorithm. Now, to summarize this part of the talk, and I will talk a little bit about something else, what I was originally planning to speak about next. But to summarize this part of the talk, in the future, all non-trivial software systems will include learning modules. So how do you engineer these systems to be safe and reliable? This is a big question. And I think that this idea of metacognition is very powerful when you are trying to address this kind of a practical question. And the idea that we can bring from the formal methods world is that letting the learner have access to a formal verifier. Okay, and this access can take many different forms. It can include gradients. It can include, having access to a shield synthesizer. There are many different ways to do this. But this overall idea of having a verifier inside the loop of a learner is very powerful. And there are, of course, lots of challenges. How do you make the learning reliable? Because it turns out that there are some complexities that come in when you bring in these extra pieces. Like, for example, in the first part, I talked about using these ideas from reinforcement learning. But reinforcement learning is hard. We like to avoid it for a reason. And so how do you improve the reliability of learning? That's a challenge. And then also just symbolic verification and synthesis has traditionally been difficult. It's a hard problem computationally, and now you're saying that you're going to do it over and over again from inside a learner. So how do you scale things? These are all great questions to address, but I personally think that in spite of those questions being open, there is a lot of promise here. How much time do I have? Okay, great. So what I'll do, sure. Yeah, so I'll maybe speak for maybe 10 minutes more. So the thing that I originally wanted to tell you about is this work that I'm super excited about, which goes back to this question over here, that how do you scale verification and synthesis? And what we are finding is that the greatest developments in the history of formal methods may be coming soon, and they may come because of language models. And I'm super excited about this area. So what's the context here? The context is that there's been a lot of progress recently on AI for mathematical reasoning. And this follows up on all the progress on AI for code that I'm sure you all know of. But what's important to note is that formal mathematical proofs are really not fundamentally different from programs. There are actually theorems that will tell you that proofs are programs. This is one of the foundational theorems of programming languages theory. And then the question is that can we use these sorts of language models like GPT-3 and GPT-4 to do generation of mathematical proofs? Now, there are many versions of this problem. Some of them involve more like high school level math or informal mathematical reasoning. But the version of this problem that I am going to talk about is where you are looking at these sorts of somewhat repetitive but highly complex mathematical problems that arise in the context of formal verification. And formal verification at this point, if you're trying to do this for entire systems, so for example, if you're trying to build a verified compiler or a verified Linux kernel, this is an extremely labor-intensive process. So for example, ComCert C compiler, this is one of the early major efforts in formal verification. This took 6 person-years and 100,000 lines of Coq code. So Coq is this proof environment where you can write formal proofs of theorems. And this ACL4 verified kernel, it's a 10,000-line piece of code if you write it in C, but then its verification took 22 person-years. But the outcome of this is great because there was this DARPA HACMS program, for example, where they built this drone which was fully verified using these kinds of tools. And then it was basically hacker-proof. They put a red team on the task to hack this drone, but they were just not able to do that after 6 weeks, I believe, of concerted effort. So that sounds fantastic. But then, it's super labor-intensive. But the opportunity that we have over here is that AI can really help. It can give you a massive productivity boost. And so we have been putting together a big effort in this direction. And what I'll tell you about very briefly today is this new line of work on language model agents for theorem proving. This follows up on the talk that you saw earlier today, the very nice talk on language agents. So the starting point here is that mathematical proofs of this sort, formal mathematical proofs, are really difficult. This is something that just a vanilla language model would frequently choke on. So the kind of the success rate at these benchmarks that we have for these kinds of tasks, it's pretty low at this point, even with GPT-4. And so here's an example. So the theorem that you're trying to prove over here, the details are not really that important, but I'll just tell you what the theorem is. So what that's saying is that if a number is even, then its square is also even. And then if you write a proof of that in your using the lean proof environment, which is like Coq, it's a formal proof writing environment. So you will write a sequence of tactics. And so what these tactics will do is that they'll just simplify the goal into simpler and simpler and simpler objectives until you hit QED. Think of it as you're finding a sequence of simplification steps. Now, if you use GPT-4 to try to do this, it's going to, I can say pretty confidently, suck in most of the cases. But the good thing is that in this setting, you have something a lot more than what you got in the language setting. Because proving, you need to see, is really a video game. You are ultimately getting a very crisp ground truth signal. You either have hit QED or not. And at each point of time, as you are applying these tactics, you are going to get information, very solid information from the underlying proof environment about what the exact goals are that remain to be proved. Okay? And so why not use that? Why just treat it as just a generative language modeling problem, and instead, why not have this sort of an interaction or explicitly model the interaction with the underlying prover? And so this leads to a picture that looks like this, that you are starting with a person who is giving a problem statement, and then you have a policy, which in this case is a language model, but it can also have extra information. For example, it can have a local memory. And you are interacting using this policy with the external environment. That would be this Coq or lean. And at each point, you're applying a tactic, which is the simplification step. And then you are getting back a signal about what's the next proof state. What are the proof goals that still remain to be solved? What are the current hypotheses? And not only that, it's rare that you do mathematical proof without any kind of external knowledge. So why not have a lemma repository, which is this external book of all possible proofs that were ever written, and you can query that as you are generating the proof using the policy. And you could even imagine discovering new tactics and forming a tactic library as you see more and more mathematical problems. And so in recent work, we built a first version of this. We don't yet have the tactic discovery part, but we have a lot of the other pieces. And the idea over here was to couple a proof search algorithm, which is a stateful algorithm, right? You're keeping track of all sorts of failures that have happened in the past, to couple it with an LLM and a retrieval mechanism. So the LLM is deciding what are the tactics you are going to apply at every state, and it's also deciding what sort of retrieval query to issue. But then you are getting back a bunch of information from the external world, and also you're selecting a tactic, and then you're executing it in the underlying world, and then you're getting back feedback from the underlying world, which is the lean or cock environment, and you are repeating this process. So now there are details over here that how do you actually set up the prompts and all that. There are details. This is kind of what it looks like. So the prompt includes a serialization of the current state. It includes a stack, which is captures basically the history. And then the LLM responds with some information about what tactic to generate, and then you parse it, and then you execute that. So what we found is that this overall strategy, it works quite well. We are using GPT-4 just zero shot, but it seems to beat state-of-the-art fine-tuned models. And as the underlying LLMs get better and better, this is just going to get better. So what this says is that, maybe this is a good example. So on the x-axis, you have the number of queries that you're making to the LLM. And on the y-axis, you have the number of proofs that you're doing. So since we were using GPT-4, we were only able to use a limited number of queries. I already paid OpenAI more than $2,000 for this paper, but I couldn't pay any more. But you see that it just goes up like crazy, right? So with a very small number of queries, you get a pretty sizable number of proofs. Whereas this is the blue curve it's a state-of-the-art theorem prover that was released earlier this year. And I'll skip this one. So we have a lot of interesting proofs that seem to be coming out of this. And this is just the start, right? So I think that there is a lot more can be done. This idea of using language agents, it's a very natural fit for this theorem proving context, which is, again, a video game. Actually, when I was a PhD student, I saw many of the best minds of my generation. They, play this video game for 5 years and then write one big proof as part of their thesis. So maybe, we can do better. Maybe we can make this more like a thing that you do in a course project. The main ideas so far are that using this sort of proof environment feedback, and you can complement this with hand-engineered search heuristics as well. We, in fact, do that, although I didn't go into details. But there are lots of challenges. One big issue is that you need to have these high-capability LLMs, like GPT-4, and these are currently expensive. And many kinds of proofs still seem very hard in spite of using GPT-4. But again, this is a start. I think that this direction is really exciting. And the biggest hurdle to the deployment, the widespread deployment of formal methods has been its labor cost. And I'm really hopeful that these ideas are going to make them a lot more easy to deploy. And then, just connecting the loop, you can imagine then, formal methods that is accelerated by machine learning, specifically these sorts of language model approaches, being used to verify machine learning systems. So then you have, machine learning for formal methods for machine learning. And in the future, when all non-trivial systems will have machine learning in them, you would need to have a view like this, in my opinion. And with that, I will end this talk. Thank you.